Welcome to Mandatory Experiment 9.2. Here we will examine the effect of changing concentration and temperature on the rate of reaction between sodium thiosulfate and hydrochloric acid. First of all, let's take a look at the reaction taking place here. Sodium thiosulfate reacts with HCl to produce sodium chloride, sulfur, sulfur dioxide, and water. This experiment has two components to it. One where we change the concentration of the reactants to affect the rate of reaction, and the second where we change the temperature to affect the rate. Both experiments use the same experimental setup for the most part, so we will examine the common method they share first before looking at the two individually. The most important part of this equation to remember, as it is always asked, is sulfur, which forms a pale yellow precipitate as indicated by its solid state of matter in the equation. As the reaction proceeds and the sulfur precipitate starts to accumulate, the solution will start to become cloudy from the sulfur suspension, and the solution, which started off being transparent, will become yellow, and it will be no longer possible to see through it. It will become opaque. This is our approach to measuring the rate. Since the faster the rate of the reaction, the faster the sulfur is produced, and in turn, the faster the solution will change from transparent to opaque, we can therefore use the rate at which the transparency is lost to measure the rate of this reaction. In our experimental setup, we approach this by putting a piece of paper underneath the reaction mixture and drawing a cross on it, usually in a strong colour like red that will be easily distinguished from yellow. We mix the sodium thiosulfate and hydrochloric acid together in a conical flask and place it on the cross before starting the timer, and we measure the length of time until we can no longer clearly see the cross through the increasingly yellow solution. We can then repeat the process, changing the concentration and temperature of the reactants to see how the rate is affected by these variables. It is very important that we keep all volumes constant and that we use the same vessels between trials where we change the concentration or temperature so that the depth of the solutions doesn't change. Here you can see how different shaped vessels might affect the result. Each vessel contains the same volume of reaction mixture, but because of their different shapes, they produce a different depth of liquid through which the observer will be looking. As the reaction happens and the solution changes colour, we can see how this depth of liquid will affect the result. Remember that the same reaction is happening at the same rate in all three flasks, but the different depths of liquid are giving different apparent rates. The vessel with greater depth on the right will require less precipitate and therefore need less time to obscure the cross. This gives an apparently faster rate of reaction. We can consider perhaps the conical flask in the centre to have an arbitrarily true rate of reaction. Its cross will obscure next. The vessel on the left with the least depth of liquid will take longest to obscure, since it will require more precipitate and therefore more time to obscure the cross. It is important to recognize that the data we are gathering here is simpler than the data we have seen in previous experiments. In all the other videos in rates of reaction up to now, we have gathered data on the volume of a product or the mass of a product over time to give curves like this one. These graphs give us a lot of information. How much gas has been produced by a certain time or by the whole reaction. We can find the average rates of reaction and also instantaneous rates of reaction for any time point during the reaction. These curves also allowed us to compare reactions under different conditions as they happened in parallel. In this experiment, however, for each trial of the experiment, rather than having multiple data points, we simply have one data point, the length of time for the cross to become obscured. How will this give us the rate of reaction then? Well, it stands to reason that the longer a reaction takes, the slower it is. If you double the time a reaction takes, then the rate is halved. And the shorter a reaction takes, the faster the rate. If you halve the time, then the rate is doubled. In other words, rate is inversely proportional to time. This gives us an interesting unit for rate of reaction, 1/seconds, or seconds to the -1. It is not very different from previous units we've seen, of course, since then we were measuring something per unit time, centimeters cubed per second, for example. Here, since we are only measuring the time, we only use the per second part of the unit. This is an important unit to remember, as it will give the unit for rate in these experiments. So in summary, to get the rate from a simple time measurement, we simply get the reciprocal of the time. Here you will have 5 different concentrations of sodium thiosulfate that you will mix with a constant concentration of HCl. It's very important, however, to understand how these thiosulfate solutions are prepared, as it's very often asked in the exam. Also, since we are measuring how long it takes for the cross to become obscured, remember that it is very important that we keep the total volume of the reaction mixture constant from one trial to the next, and that we use the same vessel. In this experiment, our thiosulfate solution will always have a volume of 50 centimeters cubed. Our first concentration will be just sodium thiosulfate, and the other 4 will be mixed with different volumes of water to give increasingly dilute solutions as shown. Here the thiosulfate solution is coloured dark blue for clarity, but of course in reality it's colourless. Let's say that our starting concentration of sodium thiosulfate is 0.1 molar. It makes sense to dilute each successive solution to 4/5 of the concentration of the original solution. To do this, we will need 4/5 of the original 0.1 molar solution and 1/5 water. So if we are keeping a constant volume of 50 centimeters cubed, then 40 centimeters cubed of the first solution and 10 centimeters cubed of water will give us 4/5 of 0.1 molar, which is 0.08 molar. To get 3/5 of the original solution, 0.06 molar, we will need 3/5, 30 centimeters cubed of the original solution and 2/5, 20 centimeters cubed, water. We continue in this way as shown to get the remaining concentrations. These solutions will then be mixed with HCl. Note that the volume of HCl is constant throughout, 10 centimeters cubed. This will mean that the total volume of the reaction mixture is constant, so the depth of the liquid is not an issue. It will be 60 centimeters cubed in each trial. We can then measure the length of time required for the crosses to become obscured, as we saw before. You will see a trend immediately that the most concentrated solution is the first to obscure the cross, and the least concentrated solution takes the longest to obscure the cross. We can then find the rate for each concentration by getting the reciprocal of the time. Note again that the rate is measured in seconds to the -1. Lastly, we will graph these values with the concentration on the x-axis and the rate on the y-axis. Note that the variable we are changing, concentration, the independent variable, is on the x-axis, and what is changing as a result of this, the rate, the dependent variable, is on the y-axis. This gives us a straight line that passes through the origin. This means that rate is directly proportional to concentration. If we double the concentration, we double the rate of reaction. We can use collision theory to explain this. At greater concentrations, there will be more particles present, and so there will be a greater frequency of collisions, which in turn will lead to a faster rate of reaction. You will typically be asked to draw out the graph in the exam. As always, don't forget to use graph paper, label the axes including units, draw all the points clearly, and in this case a straight line through the points and the origin is appropriate. In questions on this experiment, you would typically also be asked to predict how long it would take for a reaction to reach completion for a given concentration of sodium thiosulfate. We would do this as shown by bringing a vertical line from the x-axis to the trend line and across to the y-axis to find the rate. Here, for example, a concentration of 0.05 molar thiosulfate would have a rate of 0.01 seconds to the -1. To find how much time this rate will take to complete the reaction, we can of course divide 1 by the rate, so 1 divided by 0.01 to convert back to time, and we get 100 seconds. The second part of this experiment looks at how, rather than changing the concentration of the reactants, how would changing their temperatures affect the rate of reaction. Here our independent variable is temperature, and we must find a way to accurately control it. The simplest approach is to take our separate solutions of HCl and sodium thiosulfate of fixed and equal volume and heating them on a hot plate until the required temperature is reached. We can then mix them in the same way as before and record the time for the cross to become obscured by the sulfur suspension. We can then calculate the rate for a given temperature, and we can repeat the process for a range of different temperatures. A typical set of data is shown. As before, the time recorded can be converted to rate by getting the reciprocal of the time values. Plotting these values will give the curve shown. Note that the line does not go perfectly through the data. In fact, these lines rarely go perfectly through all the data points. Here our curve is exponential. We see an exponential increase in rate with increasing temperature. It is worth remembering that for every increase of 10 degrees Celsius, we see an approximate doubling of the rate. We can again explain this using collision theory. Since reactants are at a higher temperature, we will have a greater frequency of collisions as particles are moving faster, but also, and more importantly, a greater number of collisions can easily reach the activation energy. Both these factors will increase the rate. Typical questions here will again ask you to predict what the rate will be at a given temperature from the graph. As before, we will simply draw a vertical line from the temperature specified, 35 degrees for example, and find the rate on the y-axis. The time can easily be calculated from the rate, of course, by getting the reciprocal. Because of the exponential relationship here, it has been asked in the past what temperature change will be required for a doubling of the rate. Here you would choose two rate values, one twice the value of the other, and find the temperature difference. As we mentioned already, a 10-degree change is generally considered to double the rate, so your answer will generally be around 10 degrees Celsius. That's it for this video. Have a go at some of the past paper questions.